All right, so we're recording. This is, I think, the 7th lecture, and we're going to finish, as I said, discussing this chapter. The next one is centroids of moment of area. This is something you saw in statics, and I'm going to assign a computer-based. There's hand calculation involved, but computer-based assignment on area moments. Okay, so I started saying that for just concentrated loads, the shear diagram is constant between the loads, and there are abrupt changes on the diagram at the load. All right. On the moment diagram, you're seeing that the slope of the diagram of the moment diagram is the in value is the shear diagram. Actually, units including. And then where the changes, we have, of course, cusps. And then when where the shear diagram goes to 0, you'd expect a minimum or a maximum, local at least. The difference between global minimum and global maximum, and local maximum, global minimum, and local minimum. So here, yeah, we have a minimum, which is also global, or rather maximum, which is also global. But it's where the shear diagram goes to 0. Make sure when you draw your diagrams, you of course start with the load diagram and put the reaction, identify first the reaction forces in your diagrams to be aligned with the load. So things happen at the load, all right? You should verify that the reaction of the supports are correctly calculated. So the shear diagram will close to 0, and moments diagram close to 0, unless, could be the case where I have a concentrated moment at the end, case in which it closes to 0 only after I pass there too, after I pass the end, you can assume a fraction of an inch pass point F, then it should be unloaded portion of the beam. Diagrams all will go to 0. Okay. And there are some rules that we learn about. So if internally and working on the left-hand side of the beam, so again, you just section through the beam and you do free body diagrams of that left-hand portion of the beam where we did the cut. And you show the internal shear force and bending moment that holds it in equilibrium together with against the externally applied load. So if the shear diagram, or rather the shear force on the cross section is down, it's pointing down. The diagram moves up. When it comes to external loads, though, if the external force is up, the diagram moves up, and if the external force is down, the diagram moves down. All right, so drop by the amount of 3.5 kilonewtons, drop by the amount of 4.3, and it can go, as you saw, it can be both positive and negative. Likewise, moments can go both positive and negative, but you correlate the slope with the shear diagram, more slope, less slope, but both positive, and then it switched to a negative slope, and then more increased slope, also negative, and the most abrupt section of the diagram. If you want to evaluate the moment anywhere, you just, so say I could draw, so say I want the magnitude of the moment will be 0.4 plus a half distance 0.6. So what's the magnitude of this moment here is going to be equal to the area on the curve. If I want to know the change in moment between 2 points, could be where things happen or could be elsewhere. So the change of moment, which is from here to here, that is this piece, is going to be this area. If I want to know what the change of moment is, and again I delimit, say for some reason I want to investigate 0.1 of a meter somewhere here, so the change of moment will be equal to the area corresponding to the that interval. Is it clear? And it's called the area method, and it's very lucrative. We're going to use it quite a bit. We also learned that there can be distributed loads on diagrams. All right. So distributed loads cause the, and I need to look at some example. Distributed loads cause the shear diagram to change degree. So if you have an even distributed loads, the shear on one hand, you need to calculate reactions, and this is something you've done in statics. You assume just to evaluate reactions. The behavior of the beam is different. So you have a force and you spread it over a length. So between a concentrated force and the same force being distributed, the beam responds differently. The beam is happier when the load is distributed. Even discussed, like, you know, when they search for mine or tracked vehicles, they spread their weight over a wider area and they don't sink into the ground. So likewise. Okay, so if I have a constant distributed load, units of force per meter, the shear diagram is going to have a slope. That value there says 1,500 Newton meters. That's a negative value, actually. You can have distributed load from below. Think of an airplane flying. You know, because of the airplanes fly because there's distributed loads coming from the pressure from under the wing. So I think they still do this, but over time, or they're just flipping the entire and maybe airplane, and they're putting sandbags on the wings to see if they hold. Okay, so that's actually a negative value, and this slope is the negative 1,500 Newton meters. And then if you go from shear to moment, remember before we had like lines, straight lines, but with slopes. Here I have parabola. So I went from, you know, originally was, or when with distributed loads, I just have sloped straight lines. Could be straight if it's a constant moment. Case where the shear diagram, so if the shear diagram is zero value, then the moment is constant. So it goes to a parabola. And then I can have, we'll see examples where the distributed load is tapered, like linear, not constant. And the shear diagram is a parabola, second degree polynomial, and the moment diagram is third degree polynomial. All right. But the same applies. If I want to know what is the slope of around this point of this line, I read it here. So if this is 3,000, the slope around this point on the moment diagram, I read it here. Shear diagram goes to zero, the moment goes to a maximum or a minimum. Could be global or local. And then you see here the transition. So between the linear shear and the constant shear, I switch from a parabola to a straight line. Left and right of this point, the shear, like infinitesimally left and right of this point, the shear is negative 3,000. This is a continuity of tangent. So this is zero order continuity when the points match. First order continuity is when the first derivative match. The second derivative is not the same left and right of that point. Okay, and again, it went to zero where the beam, and because let's say you continue an inch to the right, there's no load on the beam. So both diagrams went to zero. It doesn't mean that you force them to zero. It means that, you know, your analysis should confirm this expectation. Okay, we sometimes for convenience, we sometimes go from right to left, but when you go from right to left, signs flip. Okay. So if I want to know, for example, what's the magnitude of this piece of the moment here, we can go apply area method, you know, what's the area here, 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 up to the point, or I can go the other way, but take it, and it was there a sign, and take this, the flip sign. Does it make sense? So I take this area, which is a negative area, and evaluate it, flip the sign, it gives me a positive moment here. Okay, in terms of the slope, well, slope is the same between B and C. that's going to be this value here. Okay? So remember, the book goes through the process of explaining how the area method, there's a proof for it, taking the infinitesimal piece of material that you're analyzing, and then you integrate between, could be the origin or other convenient points, but usually we start from the all the way to the left, and we call that origin, and then we define an x, a current longitudinal coordinate that positions a current section along the beam. Sometimes you'll see problems of this, represented like this. If you solve a practical problem and you feel like you would start from C and go to A, nobody stops you from flipping the graph. But if it's given like this in the problem, of course, you need to finish the problem in the way it was presented to you. So this one has an overhang, as you can see, has an overhang. This is a support. This is a support. This is where we have the second degree curve for the moment. We have a zero here. We have a minimum, and it's a cusp with a cusp. Here it's a smooth minimum, is where the shear diagram goes to zero. So that kind of matches. And again, you align with the loads in the beam, your diagrams. I sometimes can tell students that copied solutions from whatever, somebody else or from whatever source, because they don't, they copy the drawing, but they don't align the graph. I'm just telling you how I, my kind of secrets of, let's look a little bit of at the, wish I had a graph over there. So there's the generic diagram or infinitesimal piece of material that we study the equilibrium of, and then we integrate. I need to go back to where it looks. Oh yeah, and we need to discuss beams with or cantilever. The method of three moments for statically determined beam. I'm not going to cover it. So if you delimit out of the beam and you have concentrated moments, so you delimit out of the beam the short, like delta x. Again, we measure x from the left, like you saw it in other classes in calculus, or when evaluating area moments of inertia. You did this in statics. So we have dx here, and then we have a distributed load. And again, this is assumed negative, and it has its own, so distributed load is function of x, okay? And then I'll see a shear force, positive on this side, negative on this side. Of course, your shear force is going on internal to the beam, not on top. That's free surface. And then we have the moments that holds us in equilibrium. Okay, so without it, you don't have equilibrium. So when it's m at location x, as I move dx to the right, I have m plus a dm. Okay, so this is the equilibrium of or the beam. And then I can do, for example, I want to know what v is. Okay, so this is v, and this is v plus a dv. All right, and it's due to this being non-zero. And so I write equilibrium for the element, first for forces. So we'll say negative W of, and then I have what? I have plus V negative V plus dV, okay? So I wrote the equilibrium, and this will be W, I'm sorry, I need to say W times dx. So the resultant of this piece of distributed load going down, this V positive, this other piece negative, equals 0. Okay, so I'm interested in v, and v goes out. I have dv. So go on and integrate integral from 0 to a current x. I'm sorry. A lot of coughing on YouTube now. Of negative w dx equals, it will go negative. We'll go negative from 0 to x dv. All right, so I can change this to positive. Okay, and then doing this, it can be a constant value in case it pulls in front, but can have a other shape, could be a parabola. Actually, a good approximation of contact forces, because concentrated forces are an idealization. In actuality, it's spread over a short area. So if you have on a shaft, a pulley, okay, and there is a force coming from the belt, you actually have an area of distributed force over the width of the hub. Does it make sense? Okay, it's not, again, a concentrated force applying a point, that's an idealization. And if you want to go to an extreme, you can assume, all forces be distributed. Anyway, so we have this one, and this part of the integral is going to just be v at x plus a constant of integration. And here I'm integrating over the shear diagram. And if it's a constant, or you deal it with it's linear or constant, then this takes a specific form, and you can solve for essentially v as function of w. If it's missing, then this constant of integration is just going to be the last of the sum of the concentrated forces to the right. And I can write moment equilibrium. So this was for sum of forces equals 0 in the x direction, and then I can sum moments about the center of the element, and we can have so assuming positive counterclockwise. So, or we're going to say negative m, this is 1, plus m minus dm. All right, and then I also have to include the moment caused by these two forces. Is it the center? Actually, it's better if you do it about this spot. So it's going to be then times, and it causes a positive moment. So I have negative, assuming positive for moments this way. So it's going to be negative v plus dv, okay, times dx. So if I sum moments about this point, then this v by itself, shear force, does not have an arm, but v plus dv has an arm of dx. All right, and this is equilibrium. So now I have m goes away, and I'm getting to, I can relate now. So would be what? So I'm just double checking the orientation of, so negative m, positive m. Yeah, this was supposed to be plus. Okay, so I have dm now equals, move this piece to the other side, is going to be v plus dv dx. Okay, and then take integral from 0 to a current position, 0 to a current position. Again, if you want to draw the diagram. And you will see for deflection, we're going to go through these steps, actually moving forward to deflection and slope. Okay, that's for later chapters. So it gets you from here, it gets you m at x plus a constant of integration equals to, what would that be? Integral from 0 to x v dx. And then this being small, dv dx are like two very small amounts that you multiply, you just ignore them. Okay. So yeah, this is the equation that relates moment to a change in. So this is nothing but you can I integrated from 0 to x, but I can integrate between 2 points on the diagram. So if I do, I'm just going to get, what it was called as moment change over the diagram equals to the area. This is area under the V curve. Does it make sense? All right. Okay, so that was the most general formulation that you can think of, which captures all aspects, including of not having a distributed load, or when the distributed load is, it's a higher order. I told you, for shafts, having pulleys or hubs attached to them, a parabolic shape of the force spread over the length of the hub is a better modeling of that loading. With the discussions, so again, the method of 3 moments, we're not going to discuss it. That's for statically indeterminate. For our problem, we can use deflection and the tables at the back of the book to solve the same problem. All right, but if you have a cantilever, remember, firstly, get the reactions at the support. There's always going to be a moment in the reaction force. If this is at some angle, of course, you need to balance it at the support. And then you have, it starts with, assuming this is positive, and it is, you have a jump in the diagram from nothing, I can assume an inch of free beam. So nothing, jump, and then linear drop. Again, because most of the distributed loads come from above and they are due to weight, they never say this is negative 30 kilonewtons, but it's negative to us, okay? Because this is a negative slope and it should match this value if it's linear. Does it make sense? Do you understand what I'm saying? So even if it shows on the diagram at 30 kilonewtons, if it's above, it's assumed that goes down. It's like distributed load due to snow or people on a bridge. Many people or cars, say you have a rush hour and it's a traffic jam and the bridge is full of cars. You can model that with a distributed load. Okay, so yeah, this would be, the slope here would be this value, and of course with its sign. Between B and C, the shear diagram is constant. I don't have distributed load, so it stays constant. And it's where, it may be helpful to go right to left. But again, you need to flip sign. So if I go from right to left, this is down, but it shows as a positive number here. Again, external force that's are up rise our diagram. Internal shear that is down shows as positive on the diagram. Okay, and then you have the moment, and it starts with this moment, which is a -1. That's why you begin with a negative value. Remember, an external moment that is counterclockwise causes the diagram to drop by that amount. Of course, I go from 0, I drop this amount, and then, this was linear. This would be second order curve, and then here continues like a straight line with same value left and right because I don't have any moment, external moment applied to the beam. Okay, and then if the concentrated load is tapered, first degree curve straight line, then you would have the shear diagram. Remember, there is an integral, so you have this going. You can even write the equations. Oftentimes it just says this is a piece. This is the magnitude here. It goes to 0 at this distance. Beam can continue. So yeah, we have linear. It goes to parabolic, and the moment is going to be a third degree curve, a cubic. Okay, let me know if you have questions. But the correlation and area method works. So second degree curve, if I want to know the magnitude other than integrating and getting the actual equation of this curve. So if I want to know what the magnitude of the moment is, say, I don't know, at a distance of 2 feet from the support, I need to evaluate this area. Okay, and for that we have, instead of me, I could. What page was this? 313. So if you go to the back of the book, the appendix 1 shows graphs of shapes, including pieces of parabola. All right. So this is where you would go to like area under the curve, the centroid. Does this help us? A more extended, like there are engineering tables that also show pieces of parabolas, maybe even cubics. So you know these two heights, and you know the distance. It can tell you the area. It can tell you the centroid. All right. So this is a place where you could find information that you can use to handle maybe distributed load that is magnitude or of the type other than linear. Centroids, and page was 313, we said. Right. Come on, 1313. And then the book discusses, so this was it, this is where we were. I said that if you want to know like the magnitude, or if you want the magnitude of the shear force here, it's just going to be equal to the area under that curve, magnitude of shear. If I want to know the magnitude of the moment here, I need to evaluate, maybe integrating. So you derive the equation of the shear diagram, shear force, and you integrate between the same points, get to the magnitude of the moment right there. Okay, and then the book goes to discussing beams, or rather bend beams, and I have here two examples. So this will be one. It's like a what? Like a basketball. What do you call this? Hoop. Yes, and with a panel and everything. So if I have a force to the end that's applied, this is fixed end, and I have a force acting. The two will bend. I can analyze them individually. And what is the method of doing it? You isolate first. You go from the load to the support. So yeah, we can find the reaction that the support will be F pointing up, and then I need to, because this has a tendency to rotate, I need to show. So yeah, this is like having an incastration. So there will be a moment to compensate, moment equal to F times A, that needs to be developed into the foundation. So you separate just this piece and you analyze this as a horizontal cantilever with a down force. Okay, so like we saw it before, you just assume this to be, fixed into a wall. You find the moment, and of course the moment will be equal to A times F, in acting this way, counterclockwise. And so you move the force at the bend, will be like a compressive force, but then you have a moment that goes counterclockwise. So the horizontal beam is like a cantilever, and then the vertical beam is a cantilever that has a moment applied to its end, a compressive force and the moment to its end. Does it make sense? So again, you take pieces, separated conveniently. You need to analyze the system as a whole, and then you can analyze them individually. Again, the moments transmit at bends. Forces, they may turn from bending force to compressive force. So as I move this force here to add or to capture the effect of the offset, so I'm saying the compressive force and the moment ending at the end. This beam is subject to a moment, like a cantilever with a moment at the end only, and the compressive force. All right, so it shows what I was telling you, analyzes a cantilever, and then this is a compressive force and the moment that was, I think I said counterclockwise, but it's clockwise, in the direction of the moment caused by this force. So it tends to rotate, yeah, clockwise. All right. And another example, and this force is at some angle. and we isolate, could be just this piece, or if we want to analyze, we go in steps. So I analyze this one, and then the rest of it. Or if I'm interested just into the big piece, or the long horizontal piece, what is this delivered to the horizontal, or the long piece ABC from this L-shaped piece. So I see this same force there plus the corresponding moment. So if I move the force elsewhere, I need to add, what happened. Wasn't along its line of sliding. I did some horizontal vertical movement. Well, you can work with components. So I take this component, place it here. Again, we're talking about the long horizontal ABC piece. Take this, move it here. Take this, move it here. But because I shifted, I need to introduce a moment that is 0.6 times the vertical component. And because I shifted in line, I need to add a moment the other way, which is the horizontal component times this distance. Does it make sense? So moving a force along its line of action does not change the effect. But if I move it parallel to itself, I need to add the moment that was eliminated or created by changing the line of action of the force parallel to itself. Okay, and this is what they do. They work in steps. What was it? The horizontal piece, the in-between piece, and the final one. And you could see it will be the same values for the force, but then was a moment that came up from the force being the horizontal being shifted up and the vertical being shifted to the left, and that will be the sum of the two moments generated. Okay, and this was it. Then this is just charted ground. Just a note of warning. So bad thing can happen at joining. I keep on saying. So you can have and this is where more careful analysis, if it's an important piece, may have to occur. So you have a weldment, you have a joining, and the rest of the part may be okay, but that's where problems can develop from just a practical perspective. What's boxed in, and I actually derived the equations are behind, are what I consider more important stuff. We're going to see these equations and taken 2 steps further, because the next one, integrating, gets you the deflection equation of the beam, and if you integrate one more time, it gets you the slope. And you can apply it, including for beams that have non-constant cross-section, like stepped shafts or shafts with taper. Okay, so I guess this is it. We can try some problems and review the theory as we move along. So there's some they're really easy because of symmetry, but on the list of recommended problem, I have 1, 2, and 5. Okay, so let's do problem 5, and I'm going to blank the screen and raise the projector. It's not nice now that you can move the projector with the also with the button on the wall. So problem 5 is in problem 5 we have a simply supported beam with 2 forces acting down, and we need to show or draw, or rather first find the loads at the supports and then draw the shear force and bending moment diagrams. Okay. So says write equation for all segments of the shearing force and using the guidelines. We can write equations if we need. So chapters 5 and equation problems 5. Okay. So no, I'm sorry. I was looking at figure 5.2. We can do 5.5 after 5.2. So I was looking at figure 5.2, so I changed it to 5.2, where we have, and for this one, it says draw the complete shear force and bending moment diagrams with the techniques learned in the chapter. So Again, if you want to take over lecturing, I'm fine with that.
Are you doing problem 5 2 or 5?
I'm doing 2, and for 5 we need to derive equations. We can do that too. So for this one, the figure is 5-2. So figure 5-2. I read the text above, but the problem is 5-2 as the name of the figure. And this is a simply supported beam. And we have 6 inches. And then 2, the first of the loads. And then 2 inches. And this one is 800 pounds. And then 2 inches to the right, we have another smaller force, 300 pounds. And this is 2 inches again. And then 6 more inches, and you get a support. 6, well, this should be about equal. Okay, and we have A, I can call A, B, C, and D. And this will be reaction at A, and this will be reaction at D. We know for sure that the reactions of A and D will be both up because the load forces are down. Okay, so what do we need to do? We need to find those reactions. I said I'm keeping the sum of force in y direction for verification. So we're going to some moments about point A to find reaction at D, and there are some moments about D to find reaction at A. My preference for just for this analysis is to have positive for more moments counterclockwise. And this again is sum of moments about A and its equilibrium. So what do we write? Negative, because the 800-pound force tends to rotate the system clockwise, so it'll be negative 800, the force, times the arm, which is 6 inches. I move to the next one, also negative. It's going to be 300 times the arm, 6 plus 2, that's 8. Okay, and then I go all the way to the end. That's the RD, the unknown, and its arm is 6 plus 2 plus 6, so that's 14. And it's a positive, so I have RD times, I said 6 plus 14 equals 0. So what is RD equal to? RD is going to be, I move everything to the right, it's a positive value. So it'll be 800 times 6 plus 300 times 8 over 14. Okay. So let's calculate it quickly. 800 times 6 plus 300 times 8 equals over 14 equals. So 514.2835, I could say 3.3 pounds. Okay. And then I move to and some moments about point D. So sum of moments about point D, likewise consider positive counterclockwise. My choice equals 0, equilibrium. So this will allow us to calculate RA. I'm not jumping to using sum of forces in y direction to find RA because I may have a mistake here. Will show up when the last step would be sum of forces in the y direction or vertical direction equals 0. Put a question mark. If it ends up very close to 0 because the round off or 0, I can move forward. Otherwise, it's useless. You invest time in drawing the diagram, shear force bending moment diagrams, when your reactions and the supports are incorrect. So what do we write here? Again, reduction point for moments is D. So I say negative RA times the full length. It's 14 inches of the beam. And I have positive would be 800 times 8 inches. And then it'll be, again, positive 300 times 6 equals 0. Okay. So RA now is going to be, I move RA to the right. As expected, both will be positive numbers. So that's at least there. We've got it, or it's confirmed by the number. So it will be 800 times 8 plus 300 times 6 over 14. So what is this equal to? 800 times 8 plus 300 times 6 equals over 14 equals. This is 585.7 pounds. Okay? So let's see what we write here for sum of forces. And it's good to have them also added to the diagram. So RD equals, we got that first, 514.3 pounds. And then this other one is 585.6 pounds. All right, so positive, negative, negative, positive. So I have positive 585.6, negative 800, negative 300, positive, the last, or the reaction at D, 514.3. All right, so 583.6, was it 0.6? It was 7 at some point. Again, this, I don't know why I put 7. This is fine, yes? This is fine. So 7, yeah, I don't know why I made it 6. I saw 7.7, 0.3. That is goes to exact 0. We round it, down and up toward, it will be 0. We'll see. So let's see. I have 585.7, negative 800, negative 300. And I'm reading already negative 314. I add 514.3, and this is 0. Okay, so we got it. We can move forward and invest in drawing the diagram. Everybody was able to follow? So you may want to watch and then take pictures rather than trying to take notes, and you miss an aspect that might be relevant. Okay, so I need the space to draw the diagrams. This can go above and below. It should go above and below. The moment diagram is going to be all positive. I told you if the beam smiles and it looks like it's smiling, I'm talking deformation. It means the moments will all be positive. But with a force coming from below, it may not. Or if I have an overhang and a force down, that will be the. But smiling beams, it's not always, they are not always apparent. Humor are of different type. There are black humor and silly humor. Is that right? So we again, external force going up raises the diagram. Internal shear is positive on the diagram on the left-hand section. So if I do a section and I look at the this piece and at this end of the beam, a shear that's down, it's actually showing positive on the diagram. The external force is causing the diagram to jump. And I start with 585.6, and we usually say V and put units here, pounds, rather than carrying units on the diagram. It's I'm going to do this over. And this was 7, by the way. Okay, so stay constant. And then where this force occurs at point B, I have a drop by 800. Okay, so I have a drop by 800. And what does that equal to? I have positive 585.7 and negative 800. This is going to be negative 214.3. This whole drop is 800. Okay, and then it stays constant, no change. And then I have yet another drop going to, so this is subtracted, negative 214.3, negative 300 equals negative 514.3. And then nothing changes. Again, this is just to show where so this whole thing is negative 514.3. And then if I have another inch of beam and I move past point D, this is going to close the shear diagram, and this is no load. Okay? And indeed, you can wait up to and if you do it systematically, this is going to be confirmed because the diagram closes to 0. If you've got this wrong, then the diagram will not close at the end. Yes?
So we're writing a solution. We don't need to write where you put the dot. It's just know that it jumps down total 514.
You might be interested in these values. You're asking me whether to place these values on the graph or not. Why not do that? Why not do that? Doesn't hurt to show that you know. So moment, and moments will be in pound inch, the units. Okay, so we're done with the diagram. I can put signs, so positive, and this is negative. Everything that's under the axis, the x-axis. Again, we're assuming the x-axis to move right along the beam from 0 to full length. That's 14. Okay. The problem 5 actually says write equations of these curves, and we can do it now. You know, I can write the equation. I put this diagram. I can put this diagram in math form, which will be a piecewise continuous function. Is that right? So I can say v of x equals, I have how many? 3 pieces. So it will be 500 positive, 585, 5.7 for x belonging to 0 to 6. And then I have negative 214.3 for x going between 6 and 8. Again, how do I start? Do I have it here like so? Where do I include the transition? Do you know what I'm saying? So do I take it up to this point? You know, it's that mathematical abstraction and forces on a point. But yeah, I can write it this way. You know, the sign belongs to. I could also say, or, you know, x less than 6 greater equal than 0 is the same thing. You want to write it this way. And the last section is going to be negative 514.3 again for x belonging to 8 to 14. Does it make sense? So this is a mathematical form for this curve that you saw there. Is this one, piecewise continuous function, constant values. Okay, let's take care of the moment diagram now. I said that here clearly we know the beam is smiling throughout, and that the moment diagram is always going to be above the x-axis. It will remain above the x-axis. What else we anticipate? We know there will be straight lines, changing slopes. So it starts with a positive slope, and then it reaches a maximum because the shear diagram goes to 0. There's a change in slope with firstly less severe, but this is negative slope and going to a bigger negative slope. Okay, so I draw a straight line. And the slope here, you don't need to write this. The slope is going to be 585.7. And it's going to reach the maximum. And this sometimes is useful to put it on the drawing. So M max, we know it's going to be a max because then the slope changes to negative 214. And then 214. And there's another drop in, let me make this shallower to where you can see the difference clearly. All right. So this will be the maximum. I know it's aligned with 0 in the shear diagram. So how do I get the maximum moment? How do I get a maximum moment? You use area principle. So the moment here is going to be the area on the diagram, because I'm interested in the change in moment between the end of the beam, or 0 the moment, and a current location, which is this one. So the maximum moment is going to be 585.7 multiplied by the 6-inch distance, and 585.7 times 6 equals, that's 3,514.2 pound-inch. Okay. Again, the slope here, so slope is negative 214.3 pounds. If I take the derivative, so if I write the equation of the moment line, And it will be piecewise continuous. We can try to write that. Okay, so if you take the derivative with respect to x, you lose, which is in inches, you lose the inches, it gets you pounds. So the slope is in pounds, because the x-axis was in units of length, inch. So as you took, so slope of m is going to be dm over dx. M is function of x. M is, we'll have pound inch divided by inch. So I have on top pound inch, below I have inch. So the slope is going to be in whatever value in pounds, which is the units for shear. Okay? All right, now I want, what will be this moment here? I may be interested in the moment, or elsewhere. So what is this moment equal to? Well, it's going to be what I have so far, area under the curve between 2 points. Minus would be 214, yes, times 2. So I have this, or do I? And I said, so it will be 3514.2 negative 214.3 times 2. Okay, so negative 214.3 times 2 equals. So this is 3085.6 pound inch, units of the diagram. I could get this same value if I take this area and change the sign. So this is, I go now right to left. Sometimes it's, it's more convenient. Instead of going 1, 2, I go with just 1. So it's also equal to negative. I change the sign because I go now right from left. The book doesn't do this, but sometimes it's helpful because it's, you don't rely on a wrong calculation, say, for this one. Or you can go both ways, and that you get different values. Means you miss something. Maybe you missed a concentrated moment somewhere, if it's present on the. Anyway, so it will be the same negative 514.3 multiplied by 6. Okay, so 514.3 negative is positive times 6 equals the same thing. 3085 point, well, I've got 8 now. 0.8 instead of 0.6. I may have missed, due to round off or whatever. But yeah, this was a diagram. So what do you do with this type of diagrams? You can evaluate what the maximum stress due to bending is. We're not there yet, but I'm anticipating. So you have the beam, and maximum bending moment it happens to be where this load is applied, and failure may occur there. You can also look for stress analysis in some locations that there's a weakness. Maybe you drill a couple of holes or something. It's a board. Not that they do this. You buy a wood beam, and there's a wood defect there, and you're on construction site, and you don't. Actually, the entire wood piece is rated based on the probability of having, the lower grade wood. They have coarse defects, and those that always stay on top of the pile at Lowe's. Everybody is digging for the better ones. Okay, so this was it. Was it clear? All right. Please pay attention. Now it's variation on the theme. We may have more forces. You may have a moment that it's a concentrated moment. Let's try to write the equations. This will be in line with problem 5 that I had in mind from when studying for the class. So for moments now, I'm just trying to write the moment equation as function of x. It will be likewise piecewise continuous. So what is the equation of this line? I'm sorry? Yeah, it's function of x. So I need to write times x. And it's going to be what? If I take just slope, so it'll be 584.7 times x for x. I can say now is between 0 and 6. Is that right? So if I make x 0, I get this point. If I make x equals, what was it, 6, I should get this value. And indeed it is. Okay? And then I move to the what is the equation of moment between point B and C. So that's going to be 3,514.2. Okay, and then negative what? The slope times slope, that's 214.3. And then I have x minus 6. Agree? So if x equals 6, this vanishes, I have the value. If x turns to 8, this is going to be 2, and I'm adding essentially this area. All right, so this is for, we can verify, for x going between 6 and 8. Agree? So again, we can verify. So if I make x equal 8, it was clear. If I make x equals x, or rather 6, I get this value. I need to find this value, 3,085.6. So 3,514.2 will be negative 214.3 times 2, and then plus, I think I've got something wrong. 3,514.2 negative 214.3 times 2 equals, okay, so yeah, it's confirmed. Actually, this piece is an area principle. So the change in moment between point B and C is equal to the area, the corresponding area between the same points on the shear diagram. And lastly, I have what happens between this point and this point. So there will be, I evaluated this already. It's 3, what is this equal to? Yes, 3085.6. And I have negative, the slope is 514.3 times x minus, what is this spot here? 8 inches. For between 8 and 14. Again, the question is, how do I put equal, less or equal greater? It's always an if. What happens actually where you have that, the force applied? And the answer is there's no such thing in engineering as a concentrated force. It's always going to be spread over some area. Okay? And you can verify. If I make x equals 14, you should get 0. If I make x equals 8, of course I get this value. Does it? So with 14 here, do I get this whole thing 0? So if I make x 14 inches, I'm at the end of the beam. I have 0 moment. This should come, end up being 0. You verify that? I'm no longer wearing that t-shirt. Trust me, I'm an engineer. All right, questions? You want to take a photograph of the screen? I can wait for that. Let's do... Is it on the list? It was a time when I was going quickly over this part because once you refresh your memory about area moments, then we can do actual stress analysis. So really, after this chapter 7, we're going through this analysis and then take the moment or elsewhere where there's an interest, and we can calculate the minimum maximum bending stresses based on knowledge of the cross section. And if you're given the type of material for which you know yield strength, you can calculate design factor and validate the design. Yeah, we're going to go over some additional process. So let's look at which one. I have some that I highlighted. I think I need to add some more problems to the list. So yeah, we still have time. Let's do a problem 15. Does it say write equations? I'm not going to do. I'm just going to draw the shear force and bending moment diagram, and that will be for problem 515. The 515 problem, it has overhangs on both ends, and it's in metric. Okay, so I'm erasing this, and again, we're going to do problem 515. Let me put the mark to where this is added to the list. So right, so there is an overhang, like I said. So the beam has one support after at 2.5 x equals 2.5, and then there is a force from below 12.5 kilonewtons, and then we have another force from below. So this is 2.5 meters. I have another one at 1 meter. Which is 15 kilonewtons. And then I have down force 2 meters later. So this could be, I mean, it follows, you know, this is what? I mean, they can be sine forces, but if you have an arrow that orients the force, no need to worry about that when you work the problems graphically. If you use right equations, then you need to be consistent about, you know, what is positive or negative for force. 8.4 kilonewtons there. And then I have 2 more meters. And then I have the reaction or another support. With this one, we can consider the sliding support. And then there's a down force at the very end. And this is 2.5 meters. 2.5 meters. And this is 20 kilonewtons. Okay. The book orients the reaction, does not show the magnitudes for us to solve it. The first one to the left, it shows us goes down. We don't know from the beginning, so we can assume a positive, and then the sign will end up being negative, and we need to flip the force. Does it make sense what I'm saying? So I'm not going to show the reaction at, let me label points. I have A and B, and I have C and D and E and F. Okay, and I'm going to show the reaction at B, R at B, and I'm going to show the reaction at E, not knowing that, we're assuming that both are positive, and if one ends up being negative, I'm going to just change the arrow. Is it clear what we have so far? Okay. So in order to calculate reactions at the supports, we need to sum moments about the supports, because it eliminates one or the other of the unknown reaction forces. So I'm going to sum moments about point B. And what do we write? So the force at A generates a negative moment. So it'll be negative. And I work with kilonewtons. No, we're not doing stress analysis. So moments will be in kilonewtons, and shear will be in kilonewtons. So I have 12.5 multiplied by 2.5. And again, this is negative because I assume counterclockwise, so negative. And then I have a positive moment due to the force at C. So there'll be positive 15 multiplied by 1. All right, and then I have a negative moment, which is 8.4, negative 8.4, and the arm of the force is the distance b from B to D. That's 3 meters. And then so I passed point D. I'm at point E where the reaction is, and the reaction generates a, what was the current orientation, generates a positive moment. So it'll be RE multiplied by the arm of the force, which is 2 plus 2 plus 1, that's 5. Okay, and last force acting is the one at point F, the overhang, and it creates a negative moment. And I have negative 20 multiplied by this whole distance. So it will be 1 plus 2 plus 2, that's 5, plus 2.5, that's 7.5. Equals 0. Do you follow? Okay, so we can now solve for RE. RE is going to be, so we keep this here and we move the rest, keep it to the left because it's positive, so we move everything to the right. So what was negative becomes positive. So it'll be 12.5 times 2.5, and then negative 15 times 1. So positive, negative, positive 8.4 times 3, positive 20 times 7.5, and then over 5. Okay? So let's calculate this quickly. 12.5 times 2.5, negative 15, plus 8.4 times 3, plus 20 times 7.5 equals. So this is 191.45. I divide by 5? I think I did. Or have I? Okay, over 5. So 38.29. This will be the reaction at E, kilonewtons. Is that correct? Thank you. So let's put it on the actual diagram. So 38. You know what the problem is? I'm trying to talk, and my Broca fights the other part of the brain that knows a little bit of algebra, and butterflies occur. I snacked something before coming to class. I cannot blame it on lack of food. Kilonewtons. Let's look at we have RB to take care of. And we're doing the same. Again, you don't jump to, unless you're really confident. And you shouldn't jeopardize the rest of your calculations on not having reactions correctly evaluated. So some moments about point E now equals 0. So let's see what we have. So put my finger at E and start to write moments. The moment of the force at A will be a negative 1. So I have negative 12.5 multiplied by the full length here. 2.5, 3.5, 5.5, 7.5. Okay, the length from A to E. 4, 5, 7.5. Or move next. I have RB, and RB, as shown, causes a negative moment about E. So it'll be RB times this distance. 1 plus 2 plus 2, that is equal to 5. And then I move to the point C. So there will be also a negative moment, which is 15 times 2 plus 2, 4. So negative 15 times 4. Okay, and I see the first positive moment, so it will be positive, the 8.4 kilonewton force multiplied by this distance times 2. All right, so that's a positive moment. And then I have yet another negative moment. I move now right of the support, so it's 20 times 2.5. Equals 0. If I missed anything, it will show up when summing forces. All right, so RB, now I'm assuming this that goes to the right was change sign, and these stays as they are, so it will be negative 12.5 times 7.5, negative 15 times 4, positive 8.4 times 2, and then negative 20 times 2.5. Okay, and divided by 5. So it's absolutely clear that this is going to be a negative value. Do you agree? I have what? This is 8.4 times 2, that's 16.8. And this is negative, and bigger will be 40, what, 50 negative. And this, so I put a negative here, and I'll remember to, I'll just say positive, positive, make this negative and positive. To, you know. I mean, you can do whatever, get the correct number. So I hate to start with a negative first. You know, that's pessimistic. You know, start with you begin negative 12.5 times 75. 12.5 times 75 plus 15 times 4 negative 8.4 times 2 positive 20 times 2.5 equals. Okay, so I've got negative 1030.7, and these are kilonewtons. Okay, so I go to the diagram, and I'm going to flip the arrow like was in the problem originally. Say it was there pointing down. What did you change it? Well, that's because the book was generous this time with us, but don't expect this all the time. All right, so I'm writing this magnitude on the graph with just the magnitude I said. So it'll be 1030.7 kilonewtons. You've got different numbers. Okay, we can. I mean, it shows up right here. Some forces in the vertical direction or y direction equals 0 is 0. So you're talking about this one, the second equation, or both? Okay, well, let's forget about assume negative to be positive. Okay, I'm starting with 12.5, put a minus in front, times 7.5. And I have negative 15 times 4. And then plus 8.4 times 2. And I have negative 20 times 2.5 equals. Divide by 5 equals. I have 3739. You're right. 37, I forgot to divide by 5 probably. 37.39 kilonewtons. 37. Yeah, I mean, way too big compared to everything else. But yeah, sign is correct. So I flipped already the arrow. 37.39 kilonewtons. Again, would have shown up here right away. So let's see, what do we have? We have to verify sum of forces in the y direction. So I have 12.5 positive, negative 3739. And then I have, so another positive 15, and another negative 8.4. And I have another positive 3829. I said positive. 3829. And then I have negative 20. Let's see if this is equal to 0. So I have 37. I mean, heck, I can punch it again. Confuse myself by 12.5 positive, negative 37.39, plus 15, minus 8.4, plus 38.29, minus 20 equals 0. So it's indeed 0. You know, whistles and bells and firecrackers. And we can move to the Don't forget this step. Don't jump to using forces. Right moment equations, they're a bit more tedious, but keep the forces for sum of forces, force equilibrium equation for verification. All right, so what do we do next? We show the shear diagram, and it will be V, and it's in kilonewtons. We'll stay with kilonewtons, not to carry zeros with us. We'll be both above and below the graph. Here I cannot, for moments now, I cannot tell the beam is smiling, so make sure you manage the paper space that you have to accommodate possible negative and positive of both. I'm aligning the diagram with the load, the shear diagram with the load diagram, because things will happen where at points A, B, C, D, and F. All right, so a straight line, that's the neutral axis of the beam, really, and I begin with a 12.5 kilonewton positive. Because of this, it's up. Internally, once I move slightly right of point A, internally I see a shear that is downwards. That's the positive. But an external force causes that it's upwards, causes a positive up jump of the shear diagram. Okay, and it stays unchanged up to point B, and then I have the drop by 3739. So I have 12.5 negative 3739. Okay, and I go to negative 2489, which is almost double, or double of what we had. So this was positive, and this is negative 24.89. Okay, and then I have, it stays unchanged. This whole thing was a jump of 3739 kilonewtons. This value here, or it went to negative 24.8. I have an upwards jump by 15. So the last value, negative 24.89 plus 15, gets me negative 9.89. Okay, and stays unchanged. So this piece, again, I'm in negative range, will be negative 9.89 kilonewtons. And nothing changes up until point D, where I have a drop by 8.4. So I said negative 8.4, and this is negative 1829. Negative 1829, and stays the same. So this is negative 18.29. Okay? And then I have an upper jump by 38, so I'm at negative 1829, and I run into reaction at E, which is positive up, so I said plus 38.29. And this is positive 20, which is encouraging because we'll close the diagram with the last external force. Okay, so, and 20 here, so this is back positive. And this whole thing is 20. And yeah, if you go slightly to the right of point E, the end of the beam, that it should go to no stress. That is, the diagram closes to 0 with this being negative down. Okay? Do you follow? All right, can we move to the moment diagram? All right, so moments will be in kilonewton meters. Again, it's not stress analysis time. Once that time comes, you need to change to Newton millimeters, to use millimeters or millimeters power 4 for area moments of inertia to get your stresses in megapascals. So moment will be in kilonewton meters. Okay. All right. Now I don't know if the diagram, and it won't. It has I'm seeing 2 zeros on the shear diagram, so I'll have 2 points of extrema, maximum, minimum. So I'm showing the diagram evenly spaced, or my x-axis. Let's see. All right, so I'm at, it begins with 0 moment, and it grows linearly with a slope of 12.5 up to point B, where there is a maximum. Okay, so I'm looking at the slope. I'm seeing also slope of 20 and slope of 24. So I need to gauge my, my slopes, trying to, guess the proportions of things here. So this is the moment at B. And we can evaluate the moment at B. Moment at B is going to be this area. So what is that area equal to? 12.5 times 2.5. And this is 31.25 positive. 31.25. Okay, so I'm at point D with the moment diagram. The slope changes to a -1 and more severe, double than this. So in order to draw the line, I need to know where to stop, right? So to get it, I need to evaluate the moment at point C. I have this area. I'm subtracting, because it's negative, this area. Again, this shows that the whole thing is negative. Okay, so I already have 31.25 positive, and I'm going to subtract 24.89 times 1. So negative 24.89. Actually, it's still positive. It doesn't go below the x. So it stays like 6.36. All right, so this one here is 6.36 positive. That's the moment at left of point C. Okay, let's move forward. So we have the slope changed to a lesser slope, and it remains linear up to point D. Let's calculate the moment at point D so that we know how to continue the diagram. So I have 6.36 positive, and I'm going to add to it the area, this area here. So it will be 9.89 times 2. So negative 9.89 times 2 equals. And yes, I've got to negative 13.24. So 13.24, and it should be with a slope that is, I had it before 24, so it needs to go to a lesser slope. Okay, it was like a knee here. I'm trying to help a little bit to where it looks, visible. Again, you'd have to corroborate information, get a diagram that it looks realistic, unless you use computers. Okay, so went through 0. The moment went through 0. And we'll go back and see at where the moment went through 0. Why we want that? Because this is where deflection is maximum. When the moment goes to 0, since deflection will be for later on, but I'm anticipating. So since the moment goes to 0, which is the derivative of the slope of the deflection, it means that the beam is going to have maximum sag here. Okay, so this value again was the moment at point D was negative 13.42. Same units, kilonewton meters. Okay. I'm still, or continue with a negative slope that it's increased to negative 18.29. Let's see what the moment at E is. So I have the last moment calculated, and I'm going to subtract further, that is add a negative area, which is 18.29. So I say negative 18.29 times 2. And this is negative 50. So, and again, the slope went from almost doubled. So I need to show that on the graph. Okay. All right, so I have here negative 50, moment at E is negative 50, and it happens to be the maximum bending moment on this beam because with a positive slope of 20, it closes to 0. And indeed, if you take 20 times 2.5, it gets you 50 positive, but I flip it because I went from right to left. Okay, so was it clear? All right, so one thing that's rather new is to find where the moment is 0. Where along the beam the moment is 0. Okay, so how can we get that? There are a couple of ways. I'm going to use similar triangles. If not, you can write the equation of the moment line for that portion. Okay, we did it before, blam, 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 and set equals 0 the moment and solve for x, and it gets you where along from the end of the beam. Again, you define the origin here and have an x-axis along the beam to the right. But I can use similar triangles. So I know this piece, it's equal to 2 meters. All right? And I have two similar triangles here, this one and this other one. So I can say 6.36, which will be this piece, over 13.42 equals this piece over this piece. Let's call this A, and let's call this B. So over A over B. Can you see what I did? Similar triangles. I'm sure you've learned of these in the latest in high school, if not earlier than that, maybe middle school, high school, early high school, junior. But then this is not enough. I have two unknowns, A and B. So I need to add to this A plus B equals what? The 2 meters. So I have two equations to unknown. Is that right? So one way of doing this is to solve for B, or rather A in terms of B. So I have A equals 2 negative B. So this is 2 negative B over B. This is 2 over B minus 1. And I can solve for B. So I take this piece and this piece, evaluate this, add 1, and then take the inverse and multiply and divide by 2. All right, so 636 over 1346. I ignored the decimal point, so this will be the 0.4725. This thing. Right, and then I have plus 1 equals, and then to solve for B, I just say, so this piece plus 1, B is going to be 2 divided by, so plus 1, I said 1 over, and then times 2. So I get that B equals, what was it, 1.358 meters. So yeah, if you want to, or position this, if you were to position this from the left end, this is going to be equal to the value that we calculated, subtracted from 5.5. So I said negative 5.5 equals, so this is 4.142 meters. Was it clear what I did? So I use similar triangles. If you like instead to work with the equation of the moment, well, we can do that too. So that's why maybe we're still in that with a group of problems where we need to write the equations of shear and bending moment. So what is the equation of the moment diagram between C and D? That is for x greater than 3.5 and then greater than and less than 5.5. Okay, so it's going to be 6.36. Okay, negative, I have the slope, which is 9.89. Okay, multiplied by, there will be x minus 3.5. All right, we have other above and below. We care just about this one. So piecewise continuous function like in math. Just to make sure, so if I have x equal 3.5, which would be like point C, this should go to 6.36. If I make x equal to 5.5, I should get negative 1342. So let's verify. So again, we verify with x being 5.5. So 5.5 minus 3.5, that's 2. And we've done this actually when calculating this value, but we can double check. So 6.36 minus 9.89 times 2 equals. Yeah, we've done this actually when evaluating this. So we have the equation of the moment between points C and D, and now we can just set it equals 0. So m of x equals 0 for the right piece of it. So it will be 6.36 negative 9.89 x minus 3.5 equals 0. And x is going to be actually directly this value. So let's see. I can erase this, put the equal sign here. Do you understand what you can watch during the weekend the video, and solve for x. So it will be times x, and then I have times 9.89. So yeah, it's 6.36 plus 3.5 times 9.89 equals over 9.89 equals. And I've got x equals 4.143 meters. 4.142. 4.142. Okay, so pretty close. Was it clear? I went too far? Too fast? Well, you can play the YouTube half the speed. You can see me talking slow. All right. Trying to, like I remember President Trower was running for presidency and making fun of a candidate, and he poured some water off a bottle. Do you remember that? Do you remember? So I don't know what he wanted to do, to add to the unusual of it some important aspect. So yeah, you may be interested in the spot where the moment goes to 0, because that's where the beam will be deflected the most. Okay, so yeah, this was the second problem. 140. We can do what? We can do a cantilever with distributed load, and for that I'm going to go to problem 540. It's evenly distributed load. Nice problems, but again, they're only like half of what is usually done for this kind of analysis. Once you have the moment diagram, you can evaluate stresses. You need to know the one equation will be the equation of all equations, and then you need to know area properties, calculate the stress at that location. Usually we're interested in the peak stress if beam is constant, but the beam can have sections of different fabricated beam. You have a board, and then you add above and below over shorter section, 2 more boards to stiffen it. Does it make sense what I'm saying? So I can take these two and wrap them, and I get a beam that's, say, it's supported at the ends, but it's reinforced in the middle. If you go to Walmart, for example, I don't know how many of you, you look for bargains, but look up and you will see frames, and you will see that they look like trapezoids. So they have the supports, but then they change to spread the material to increase the area moment. Anyway, it's not a continuous. It's fabricated with trusses, but about same applies. You increase the area moment of inertia. So yeah, it's a cantilever, and it's having distributed load. So let's see how I go about this. Don't forget the book. You pay money for it. And don't forget a sample problem in the book, sample problems that you can read with all the explanations to reinforce what you're learning in this class. Okay, so we have a cantilever with a distributed load that's even, and it's towards the outer end. So problem is 540. 540. Well, I need the markers. 540. Yeah, I need to retire some of these. Okay, so what do we have? I said it's a cantilever, and it's a 2 foot distance to the support, and then over 4 feet distance we have, so double of this, we have a distributed load of, and I put in the negatives. When it's above, it's assumed that it goes down. I show like a quiver. So W, it's in our case is 2.5 kilo pounds kips per foot. So negative 2.5. Since I oriented it, so 2.5 kilo kips. Okay, over foot. All right. So this is our problem. We need to draw the shear force and bending moment diagrams. So first thing is to calculate the reaction at the support. So let's call this A, B, and C. And then I have a moment that I can tell it's, if not, so this tends to rotate this way, the moment has to go this other way. But I'll put it any orientation I want. If it ends up negative, means I've got it wrong. So this is the moment at A, and I want them both. To get the 2, I need to find the equivalent concentrated force to this distributed load. So we had 2 feet, never added the T, and this whole thing is 4 feet. Okay, so from statics that the equivalent to the distributed load is a force equal to the area, all right, located at the centroid of the distributed load figure. It's a rectangle, so this is going to be 3 feet from the support, 3 feet. And the magnitude now is going to be 2.5 times 4. I don't even give a name to it. And I represent it dash so that it's not like, you can have a distributed load and a concentrated force there. That's also possible. Yes?
Isn't it 4 feet? It goes to the middle.
Let me look at the figure again. So it says 2 feet and then 4 feet. Yeah, you're right. 2 plus half of this. Thank you. So you corrected this. Appreciate it. So what is the magnitude? Let me take this. So the magnitude of this force shown dashed and in blue is going to be 2.5 times 4, that's 10. 10K. All right? Here you don't sum moments about two locations. We use directly sum of forces to get R, and then sum moments about, so sum of forces in the y direction gets us R, and that's going to be 10K. And then for the moment, what's the magnet of M? You sum moments about point A, where R, that you may have it wrong, does not have an arm. So it's going to be, I can say sum of moments about point A equals 0. So that will go, and I'm assuming positive for a moment as I used to. So it'll be negative M, and then negative M, negative 10 times this, that I got it wrong for a moment, equals 0. So M at A, I could even say M at A. Okay, M at A is going to be negative 10 times 4, that's 40. So negative 40 kilo pound foot. So if it's a negative value, it means that this is, didn't got it right. So what do? We change the orientation. I write MA equals 40 kilo newtons. I'll write a kilo pound foot. For the figure now, to match the equation for somebody that does not watch the video, correct, this equation is no longer correct for this graph. So I need to change this to plus, and like so. Does it make sense? So if you review, if you take a picture of this one, like it was before I changed, it was negative, and a negative here. This equation does not correspond to the graph because I changed the diagram, because I changed the diagram. So in order for this equation to match the diagram, I make this positive and this positive. In case somebody if somebody's missing class and you give them your notes, they won't understand. They get or confused, or if you take a picture. Let me see, what time is it? 1:49. I have 6 more minutes. Let's finish this. Okay, so we've got everything. Again, this was just for this analysis. This is no longer here for us. We switch back to the original problem. So let's draw the shear diagram now. So I have the horizontal axis. Shear diagram is going to be in kilopounds. And I'm at A, and I have a 10K jump, and then I stay on it, stay constant, nothing happens, up to point B. Okay? And then so I have